Hello. So today I have a interesting showcase for you. This is a puzzle that I constructed, but more like discovered. And where this came about is on the Theory and Programming channel in the CTC Discord, where Ryokusha has actually been doing a lot of work on anti-knight, specifically a combination of searching for minimal anti-knights. This is not a minimal, not by far. And he's actually found a few anti-knights with 8 givens, which is the minimum. You can prove that's the minimum if you think about it. Where anti-knights with 8 givens that are uniquely solvable, or at least have a unique solution, but none of them have been solvable so far. But his investigation and his tenacity in trying to figure out how to solve it, he's found some interesting anti-knight patterns. Um, and so this puzzle is based on one of those patterns that he found that had an interesting property. And so what I did is I put in the pattern and I sort of added rotational symmetry to it. I'll tell you about it later. Before I want to make sure you can go into this puzzle blind if you want to. Although I will say, don't try the puzzle yet. Hear my explanation first. At least let me introduce the puzzle to you first before you try it. But the pattern is in here. I added rotational symmetry, and then I added a given to make it unique, which is the 8 in the center. And then what was interesting about this is at least applying some of the what I'm calling new tech, if you want, that Ryakusha has been exploring. I believe it is on the edge of human solvable. So that's my warning. You're going to have a tough time solving this. I did not solve it myself. I used the help of some advanced features of my solver, my logical solver, as well as exploring it for quite a while in F-Puzzles. And so basically what I'm trying to say is I think every step is understandable by a human and is not by itself a ridiculous step. But there's so many of them, and finding which, where they are, I think that this is a multi hour solve if you don't get help. So you are welcome to try and solve this, but please don't come to me and say that I didn't warn you that it is probably going to be a horrific grind. So why am I presenting this puzzle? Well, I'd like to just show off some of this anti-knight tech, because the 8 given anti-knight puzzles, we don't know how to solve those at all yet, other than through computer brute force, like massive bifurcation. This, I don't think anything I'm going to do here would be considered bifurcation. Just some really interesting anti-knight patterns that have emerged. And who knows, maybe if we develop this tech enough, we'll be able to figure out something about anti-knight that will allow these 8 given puzzles to be solvable. But for now, I think this is one of the most technically heavy, somewhat human solvable anti-knights that I've seen, and so I wanted to present it. So I'm sorry for that long intro, but please feel free to just watch my solve here. I have it planned out mostly. I'm going to do my best to avoid just massive pencil marking and picking off individual digits, but we're going to be doing some of that because I think there's really no way to avoid it in a puzzle like this. But I'm going to do my best to keep this flowing well. And I might add, I might cut if I'm like, oh, I got to fill a bunch of cells. I might just cut that out. And so we'll see. But however it goes, I hope you enjoy this video. I hope you learned something about some cool stuff you can do with anti-knight, which is kind of an interesting, like, we take classic techniques, and then because anti-knight is added to the mix, you can do some really cool stuff with it. So, all that said, I'm going to get started. Let me introduce the puzzle. I'm calling this Beetle Knight. Knight is obvious because it's an anti-knight puzzle. I thought that this pattern here looked kind of like a beetle. You can tell me if you see it or not. But either way, that's why I called it Beetle Knight. And I'm going to get started now. So I guess I should also go over the rules for those who may not know anti-knight, although if you don't know anti-knight, this is going to be a little bit overwhelming. But all anti-knight means is if you think about a knight's move in chess, let's take a look at this 8 here. If this were a knight in chess, where could it move to? Well, it moves 2 in one direction and 1 in another direction. So that's these cells here. They form this kind of circular pattern. It's 8 cells that it sees. And what that means is we cannot put an 8 in any of these cells. We're not allowed to put an 8 in any of these cells because it's a knight's move away from an 8. So no digit is a knight's move away from itself, is what that knight's move means. All right, so now let's get started on the puzzle. So the first thing that I want to point out is what I was talking about before. This is the initial pattern that this was based on. You can see that I kind of tried to duplicate it here. Now I could duplicate the 3, but you can't put a 4 here. There's actually no solutions. And so I did my best. I just added the 3, 4 across. I added the 5, 6, 7, 8. I was able to put this 3 here, and then this 8 made it unique. And we got lucky with it being this interesting puzzle. So it's more of a discovery than really setting it. But this pattern here is pretty interesting because it does a lot of forcing of, obviously just the 1s and 2s. But even on a blank board with just these being 1s and 2s, you can place a bunch of 1s and 2s, which is really interesting. And we sort of figured out the logical progression for that. I'll go over that while we solve the puzzle. So the first thing we're going to do is we're going to see that this one sees these 3 cells and this one sees these 3 cells. So even without these givens, we can see that 1 would be limited here. But because we have the given 2 there, which would be given with just this pattern, we get 1s limited to these 2 in row 5. So that means none of these can be 1. That's claiming. The 2s do the same thing. These 2s see all of these cells. And then the 1 is placed here, so 2 is limited to these 2. And then finally we have this 3 here and this 3 here. And so we are able to limit 3s here. Now, this 3-4 pattern, because there's no given 4 here, it's not as powerful. We aren't limited to 2 cells, we're limited to 3 cells. But still, I wanted to mark that. And so now what I'd like to do is I'm gonna focus on specific rows and columns, and we're gonna look at where 1s and 2s can go. So I'm gonna start with column 3, and we're gonna ask where 1s can go in column 3. You might be able to see that it's actually limited to 2 places. So this one removes it from this box entirely. We obviously have the given 3 and 6, and this one removes it from these 2 cells. And so we are down to these 2, and I'm going to use blue to represent where 1s can go. And now what we're going to do is look at column 4. This one eliminates from this box, this one eliminates from these 3, and this one also sees into this box here. And so again, we're down to 2 cells here. And something I want to point out is these 2 cells see each other by knight's move. So we're either going to have a 1 in both of these, or we have to have a 1 in at least one of these 2 cells. So we could, eliminate a 1 from these 2, but they're already eliminated by the givens, so that's not that important. But I did want to point out that these 2 do see each other by knight's move. I'm also going to do column 7. So where can 1 go? Well, this one removes it from these 3. This one removes it from this one. And actually, these 1s are important because they claim the box. So we actually can't put it in any of these cells. And so 1 is limited to these 2. And finally, maybe not quite finally yet, we're going to look at a couple boxes as well. So box 4 and box 5 are going to be important for where 1s go. So I know my highlighting is going to be a little bit confusing, but in this box, where can 1s go? Well, this 1 is in the really important anti-knight spot, which removes this whole plus sign. And then this one actually does manage to peek in and eliminate 1 cell. And so 1 is in one of these 3 in box 4. And then in box 5, well, this one immediately does the plus sign thing again, and this one looks in, and so 1 is limited to these 3. So that's all I'm going to mark right now. We technically have these marked with corners 1s, but they're not going to be important for our logic. And so just remember, we've got column 3, 4, and 7 marked, and we've also got box 4 and box 5 marked. So we have some 1s up here that can happen, some 1s around here that can happen, and up here, and we're not worried about that right now. So now I'm going to mark 2s, and if you notice, the 1s and 2s are rotationally symmetric. So whatever I did on columns, I can do on rows. So the equivalent rows, we're going to be doing, the equivalent to column 3 is going to be row 7 for this pattern. So where does 2 go in this row? And I'll try to go a little bit faster here because it's basically the same as what we just did. These 2's claim like this, and so 2 is limited to these 2. And we can see that 2 is going to be limited to these 2. And similarly, 2 is limited to these 2. And finally, in this box, 2 is actually limited to the same 3 cells as the 1s. You can see these look in, that looks in. And I don't need to actually mark another box. It would have been, actually I can mark this box here. That's the equivalent. So this 2 makes a plus sign, this 2 looks in, and so these can be 2s in box 8. So what do we do with this is the question. Well, first of all, I'm going to point out the 3 columns that we marked. We are down to 2 cells in each of those columns. So I'm gonna add a little purple splash to those. I hope that's not too confusing, just to call those out. Now, we're going to be doing a lot of finned fish. I don't think we have any actually regular fish in this puzzle, but we are going to be doing a lot of finned fish. So I would like to take the time to make sure we understand how finned fish work, and we're doing it in this simplest possible orientation for an X-wing, a finned X-wing, which is the smallest fish. I don't know, X-wings aren't really fish, but we call them that. It's also technically, this one's a sashimi fish, and I'll go over what all of that means just so that we're all on the same page. Sashimi is just because there's an argument, online arguments about whether it's really a fish, and we'll go over all that. So if you have seen the Sudoku series, you'll probably understand finned fish, but in context of Anti-Knight, it's actually very powerful, and you'll find them all over the place. All you got to do is just highlight everywhere a single digit can go, and you'll probably find some finned fish in a regular Anti-Knight puzzle. So what do we mean by this? Well, first, let's focus on these 3 columns that we marked. So the purple cells are where 1 can go in those 3 columns. How many 1s are we going to have in those 3 columns? It's not a trick question. We will have 3 1s. So we don't know where they go, but we know there's going to be 3 of them. If I can draw 3 rows, and let's draw it like this. If I draw 3 rows, those 3 rows will also have 3 1s in them. So if I'm able to cover all my purple cells using rows, then... Did I say this was an X-wing? This is a swordfish. I apologize. Swordfish is 3. For some reason, I thought this was going to be an X-wing, but X-wings may come later. But this is definitely a swordfish. Sorry for the tangent there. But I can cover, if I can cover all the purple cells with 3 rows, then that would be a normal swordfish. And what that would mean is, because the purple, we know there's exactly 3 1s in the purple cells. And if I can cover them with 3 rows, then there's 3 1s in those rows. And because the purple cells would donate exactly 3 1s to those rows, the rest, the non-purple cells in those rows would not be able to be a 1. Otherwise, we'd have too many 1s in those rows. So if you didn't understand that, hopefully maybe you can go back and watch the Sudoku episode about it, so you can really, we spend over an hour on that, on all the different kinds of fishes. But that's the basic idea. However, there's a single purple cell here that's not covered by rows, which you probably noticed. So we don't have a typical swordfish. Instead, what we call is this purple cell here, this is a fin. So what I'm going to do is I'm going to mark these 3 rows as orange, just to give some color. I know there's a lot of colors going on here, but orange should hopefully stand out. And this is our fin. So what the fin is what we're saying is, well, what if this actually couldn't be a 1? What if I just cleared that out? Well, now we have a swordfish. And the swordfish, other than we can't do it on the purple cells, obviously, but all the non-purple cells would not be able to be a 1. And so I'd be able to remove a 1 from any blue-orange cell. So that would be these two. I could remove a 1 from both of those. But unfortunately, that's not the reality. The reality is this could be a 1. There's nothing stopping this from being a 1. But if this is a 1, what does this eliminate? Well, this eliminates, I mean, it sees more than that, but it eliminates from its box. And specifically, it eliminates this one here. So if there's any blue-orange cells, and I think I undid too much here. There we go. Well, I don't know what just happened, but that's what we wanted. If there's any blue-orange cells on the grid that would be eliminated by purple, then that means either purple's true, in which case that cell is eliminated, or purple's not true, in which case we have a swordfish, which still eliminates that cell. So this cell here cannot be a 1. So all that to say, we get to eliminate a single 1, but it's important because now that this can't be a 1, guess what? Now in this box, these ones point right, and this one can't be a 1 anymore. We could have also done this in a slightly different way. Let me undo a little bit. So I drew these 3 columns. I could have very easily drawn these 3 columns instead. And so now where's the fin? Well, this is the fin here, and it sees this cell. So that's the cell we just eliminated, and it does the exact same thing. We eliminate this cell here, and now these point left and eliminate this one. So you can kind of, this is called a Siamese fish, when you can draw it in multiple ways and it does eliminations in both of those ways. But we actually only needed one of them because pointing takes care of the rest in this particular case. So I'm going to clear my purples out. And so now I have ones eliminated from these 2 cells. And you probably guessed it, the 2s are going to do the exact same thing because they're literally rotationally symmetric. So we're going to have to draw columns. So first of all, we're going to use these 3 rows as our base for our, oh sorry, I cleared green from there and I should not have, for our greens. So this is going to be row 4, 6, and 7. And so I'm going to highlight the greens that are for those, and I'm just going to make those have I'll just use purple again. I'll use a purple splash on those. And again, we can cover with this column, and we can just choose one of these columns to cover with. Let's just do the same thing we did last time. Let's cover with this column here. Let's make that orange. So either purples form a swordfish, eliminating this cell, or this fin is true, which eliminates this cell. And I'm going to have to go fast on all these fishes because we're going to have a lot of these. So hopefully you understand how these work. But this fin sees this orange-green cell. That means this orange-green cell cannot actually be a 2, and we can eliminate it. So we're going to clear out my oranges. I'm going to clear out this green. And guess what? These 2 now point up, and this one cannot be green. So let's get rid of our purples as well. Just clear those out. So now we're down to this situation here. So what can we do from here? Well, I would like you to focus on these 3 cells right here. Should I give them a splash? Let's give them a purple splash here. This is probably the smallest discontinuous nice loop you will ever see. So this is referencing the first Sudoku episode, where we did go over what a discontinuous nice loop is. I think we focus a lot on the other style of nice loop more, but the discontinuous one in this case is very useful. So I'm going to explain the logic without worrying about discontinuous nice loop, and then I'll explain how you could see it as a discontinuous nice loop if you'd like to, but I'm not going to go into our alternating inference chains and strong and weak links. I'm not going to explain that. You can watch the first Sudoku episode if you're interested in what that terminology means. But let's go over the logic in a way I think everyone will understand. Now remember, blue is 1 and green is 2. So let's focus on column 3 and actually we can just we can focus on column 3 and box 5. And let's ask the question. We're focusing on these purple cells, but don't worry about purple at the moment. What is actually going on here? So I've got 1's limited to these 2 and 2's limited to these 2. So the question is, can I avoid having a 1 not in here and a 2 not in here? And the answer is no, I can't avoid that. One of these or both must actually be the 1 or 2. Because if neither of these could be a 1 or 2, then in box 5, this cell would have to be both a 1 and a 2. And, we don't have Schrodinger cells in this puzzle. So what that means is, oh, great, I have to undo all my 1, 2s. Right. So what that means is at least one of these is a 1 or a 2. So what would happen, and then the same thing's happening in column 3. Again, if one of these two must be a 1 or a 2, either this is a 1 or this is a 2 or both, but not neither, because again, neither would make this a Schrodinger cell. So one of these is a 1 or a 2, and one of these is a 1 or 2. So what would happen if this cell wasn't a 1? So let's just say this one's not a 1. Well, now this cell's a 1, which forces this to be 2. Or we can just use our direct logic and say, because this one isn't a 1, this one is a 2. Now, where does 1 go in this column? It goes here, or more, we can skip that step and say, well, one of these two had to be a 1 or a 2. This one's not a 1 anymore. That puts a 2 here. These two see each other. That breaks the puzzle. So our premise there was, what if this wasn't a 1? And the answer is, we get 2 2s that see each other by Knight's move. So this must be a 1. Now, how do we see that as a DNL? Well, if you'd like to describe it that way, well, we do have a strong link between this 1 and this 2 for the reason I described, through this cell. You could draw it through this cell if you wanted, but we can just directly say we have a strong link between this 1 and this 2. There's a weak link between these 2 2s, and there's a strong link between this 1 and this 2. So I can say strong link, weak link, strong link. We started and ended with a strong link. That means it must be true. We have to place a 1 there. All right, that's our DNL. So now that we've placed a 1 here, we can do some cleanup. This can't be blue, and this can't be blue. And so this 1 sees this cell, can no longer be a 1. So now this is a 1. So now this can no longer be a 1. So this is a 1. Those were both done through the columns, if you remember, that they were limited in those columns. Remember, this box was limited now. We have to place a 1 here. If we look at where our 1s are, we have, we've got another 1 that can be placed exactly right here. And then we have these 1s left, and we have these 1s left. So we can just corner mark these 1s, and we just have this last X-wing on 1s. So now I can clear out my blue and my purple, and we're just down to these greens. Now notice this green is occupied by a 1, so it can no longer be a 2, so we can clear that out. So now in this row, remember that green was limited in the row, so this is now a 2. So now that's not a 2. And this isn't a 2 by Knight's move, so the 2 goes here. And now, obviously in this row here, 2 has been limited, so we can place that 2. This is no longer 2. We can place this 2. If we look at this box here, that 2 is now limited to just here. And finally, we're going to end up with this X-wing left on 2. So we have 7 2s placed. 1, 2, 3, 4, 5, 6, 7. And we have this X-wing on 2s left. All right, so as I said, that's actually very powerful. Basically, this opening pattern here ended up letting us place all those 1s and 2s. And so now what we have left are we should focus on the 3s and the 8s because we have 2 givens of those 2. The other ones we just have 1 given. So 3s and 8s are going to be the most profitable at this point. So you may be able to see just from highlighting these 3s, we're going to look at row 3 and see that this 3 eliminates from its box, and this 3 happens to see these 2. So we can place this 3 here. And then now we can look at row 4. This 3 sees these 2. This 3 sees this one. These 3s look up. Or this 3 sees it as well. And this 3 sees this box. And so this is a hidden 3 right here. Now we can look at this box. This 3 looks in. This 3 looks in. These 3s look up. This 3 looks over. This 3 also sees that one if you don't want to use the pointing. So we get a 3 here. So now we take a little bit of a detour from the 3s and we focus on the 8s. for a little bit. The first question to ask is, where does 8 go in box 6? Well, this 8 sees in to... This 8 sees these two, which is important. And then this does the classic plus move here. Now that this 3 is placed, that means an 8 must go here. Now, these 8s look over, and this 8 sees in. And so the 8 must go here in row 4, or in the box, whichever way you want to do that. And so now in row 3, where do 8s go? This 8 happens to see this now. This 8 sees this one. And this 8 sees up. And so the 8 must go here in row 3. Next, we can look at this box here. And we can ask where 8 goes again. So this 8 sees in, this 8 sees up, and it sees the center cell. And these two are given. So this must be an 8. And then we just look at box 2 next. This 8 looks over, this 8 looks up, this 8 looks over, and this 8 looks in. And so that's an 8. And then we can look at box 7. This 8 looks down, this 8 looks down, this 8 looks over. That's just Sudoku, not even anti-knight. And we are almost done with 8s. We just have one more to place. This 8 sees in, and this 8 sees down, and this 8 sees over. And so we get an 8 here. And that is all of our 8s, suddenly. So now that these 8s occupy some cells, we can continue with 3s. For example, these 3s just look over, placing a 3 here. And now we can ask about row 7. This 3 sees down, this 3 sees down, this 3 sees these two, and this 3 sees down. There's only one place for a 3, which is here. So we ended up not really needing those 3 marked, but it was nice to see at the start. And then there's just an X-wing on 3s left, like so. Which shouldn't be all too surprising, considering that we had this same pattern of 3s that we had for 1s and 2s. So, from the start. The real surprising thing is that the 8s actually managed to finish, but I think it's because we got this center cell. It's not the same pattern. All right. So now there's a lot that can be done. I think the cleanest thing to do next is to look at box 1 because it has 3 cells remaining. And those have to be 4, 7, and 9. And this 4 sees over, so that's not a 4. And we can also fill 6, 7, 9 here if we would like to. And now here's where I'm going to just be magically pointing out cells that happen to be restricted. May not be obvious, but I think at this point, I wouldn't blame you if you just started filling cells in. So I'm going to point out the ones that are important. This one here, it can't be a 1, 2, or 3. 4 is locked here in this box. 5 sees it by knight's move. 6 sees it in the row. And 8 sees it. So this is just 7 or 9. And we can actually point out that these two are the same digit. I'm just going to use like a... let's use a purple to represent that there. So these two are the same. The reason is, where does purple go in this box? Well, it's not these two, so it must be this one. And so now we have a 4, 7, 9 triple in the row. So the rest of the row is 1, 2, 5. And we can see that this can't be a 1 because it sees a 1 in the box. And this cell here can't be a 2 because it sees a 2 in the column. This can be any of them. And so the next magical cell that I'm going to be pointing out is this one here. So what can it be? It can't be a 1, 2, 3, or 4. It could be a 5, could be a 6, can't be 7 or 8, and so it could be a 9. But we have this triple here. So this is a 1, 2, 5 triple. I'm going to put that in green temporarily. And you may notice that this cell is actually seen by the entire triple. These two see in the box, and this one sees it by knight's move. And so if this cell were, for example, a 5, it would remove 5 from all 3 of the green cells, and now we would not be able to complete this row. So it's not a 5. So it's actually down to 6 or 9, which is very nice. The next fun thing to point out, and this is a pattern that I think that is very powerful in Tonight. I think it's always worth looking for it once you start getting a little bit restricted. We are going to look at column 3, and I'm just going to highlight. Let's reuse green here. Let's get rid of these greens. I'm going to highlight these 4 cells here. So these 4 cells are really nice because they see the center cell of the box, all 4 of them. And that's all that's left for the column. That means that this cell, this is going to be a quadruple, and this cell cannot be any of those quadruple values. So what are the quadruple values? Well, they're 4, 5, 7, 9. So this cell can't be any of 4, 5, 7, or 9. It also can't be 1, 2, or 3. And it can't be an 8. So that is actually a naked single 6, if you believe it. So we can just fill a 6 there. And we have something a little bit similar going on over here. So it's a little bit different, though. I'm going to mark just these 3 cells as green. And we do still have a quad left in the column. In this case, it's 4, 5, 6, 9. And these 3 cells do see this center cell. Now, this cell is only 6 or 9, which means that within these green cells here, and I can get rid of these green for now, so we're not confusing ourselves. Within these 3 green cells, we must have a 4 and a 5. Otherwise, we won't be able to place them in the column. So, and they all see this cell here. So this cell, it already couldn't be a 4, but now it can't be a 5. So it is actually down to 1, 7, or 9. So the next thing that I want to point out is actually I'm going to re-highlight these in green. We're not worried about the purple cells right now. And you notice that we had these 3 greens limited to 4 and 5. Or not limited to, but 4 and 5 must appear in these greens. The same is actually true of these greens. So here we're actually going to be doing, it almost looks like a swordfish, but we're actually just going to, we're not going to even introduce a 3rd column to make a proper swordfish. We're just going to make an X-wing. So I'm going to cover, and we're actually on 4s and 5s simultaneously. I'm going to cover with 2 rows like this, which leaves these 2 as my fins. So if I've got these, let's just use orange here again. Color those in orange. These 2, let's make those blue. So the blue cells are my fins. I'm covered with orange. What do the blue cells see? They see this cell right here. So this cell right here is eliminated. And we can eliminate both 4s and 5s. So we basically have 2 fish that overlap each other here, 4s and 5s. And this cell cannot be 4 or 5. So what can it actually be? Well, it can't be 1, 2, 3, 4, or 5. And it can't be an 8. So it is down to 6, 7, and 9. Now, we're going to do a little bit more wizardry. And I'm going to point out that this row is down to 4, 5, 6, 7, 9. That's what's left. We have 1, 2, 3, and 8 used. But also, this box has 1, 2, 3, and 8 used. So it's also down to 4, 5, 6, 7, 9. All right, and we can clean these up a little bit as well. So this cell here does see a 6 by Knight's Move. This cell here sees a 7 in its row. This also sees a 7 by Knight's Move. And then we will go from there. And what I'm going to point out is we do have a lot of 4, 5, 6, 7, 9 cells in this area here. So hopefully we can do something with that. And what I'm going to point out is that we can make a quad like this, right? We can say this is a 4, 5, 6, 7, 9 quad. So we can already make certain judgments. Like we can look and see, okay, 4 can be any of these cells, 5 can be any of these cells. But what about 6? 6 is actually limited to these 3 cells in the row. And so we can do a little bit of pointing with the 6 if we want to. We can say, well, these 2 cells are in this box, and this cell here actually sees these 2 cells by Knight's Move. And so they can't be 6 because the 6 is limited to these 3. And if either of those were 6, they would eliminate 6 from all 3 of them. And then we can also point out that 7 is limited to these 4, but that doesn't do anything. But I'm gonna ungreen this one, and I'm gonna green this one instead. So now what is this? Well, this is what's called an unorthodox tuple, or an unorthodox quintuple if you'd like, since there's 5 of them. So if you think about it, can a digit repeat at all in the green cells? Well, obviously we're not getting a digit repeating in any of these 4 because they're in the same row as each other. So the question is, can this be a duplicate of any of these other green cells? Because if it's not, then there's no repeats. And you can see this sees these 2 in the box, and it sees these 2 by Knight's Move. Oops, not those 2, these 2. And so actually, this is what's called an unorthodox quintuple. It means we can't repeat any digits within it. So we can actually repeat this trick. And we can say, where's 7 go? Well, 7 is limited to these 3. They look left. This cell cannot be 7. But I can actually take that a step further. And I can say, where does this cell go in green? Because this cell is made up of the same candidates as green. And we know digits can't repeat in green. And so this cell here is not in any of these 4 cells. So these 2 cells are actually clones of each other. And I'm gonna use blue for that to show that those 2 are clones. The next thing I can do is I can actually remove this green now. And I can add this green. And guess what? This is another unorthodox tuple. The question we could ask first is, where does this cell now go in green? Well, this cell doesn't go in these 3, and it does see this one by knight's move. So this cell and this cell are now clones. I can use orange for that, or yellow, I guess. Whatever I happen to click there. There's no eliminations for that yet. And then we can also ask, where does this cell go in this box? Well, we already showed that it can't repeat in any of these greens. And I guess I should prove that this is an unorthodox tuple. I didn't actually prove that. So we have to prove that nothing can repeat. But we got 4 in the same box. So all we have to prove is that this cell can't repeat a digit in any of these greens. Well, it sees these 2 by row, and it does see these 2 by knight's move. Just like that. And so this is an unorthodox tuple. And so now we can ask, where does this go in this box? Well, it's the only non-green cell. So these 2 are clones as well. So the next thing that I'm going to ask, we can get rid of the green for now. We're going to keep our clones here. Actually, I shouldn't have used purple there because we don't know it's the same as that other purple. So I'm going to change that to orange. All right, so next what we can ask is, where does 5 go in this box? And actually, we only have 4 cells left, so we can fill in 4, 5, 7, 9. If you look, this 5 is actually doing its good anti-knight plus sign thing. So these 2 cannot be 5, and so actually we have limited 5 in the box to these 2. So now yellow can't be 5. We can just remove it from both yellows because we know they're clones. Similarly, where does 4 go now in box 6? Well, this 4 looks down. It does its plus sign thing. These 8 and 3s are used up. So 4 actually now points down, and orange cannot be 4. So we're starting to whittle down those. The next thing we can ask is, where does 7 go in box 6? Well, this 7 is actually doing a lot of work now that we have these givens. Because this 7 looks up, and it sees this cell. So 7 is limited to these 3 here, and I'll corner mark that. And the question we always want to ask when we've limited a value to a row, column, or box is, do they all see the same cell? That's pointing. And so these 2 see this one, and this 7 also sees it. So this cell can't be 7. And so it could be worth marking this cell. It happens to be worth it. So what can it actually be? It can't be 1, 2, 3. It could be 4. Could be 5. It can't be 6 because 6 is in the row. It can't be 7 because we just eliminated it. It can't be 8, but it could be 9. So it's down to 4, 5, or 9. So next is going to be another very interesting technique that anti-knight, you can do it in classic, but with anti-knight, it just exposes some really interesting stuff. So I think that this is actually doable. This is pretty easily seen. Now the fancy term for this is, at least in Sudoku solvers, they call it a region forcing chain. And so in solver terminology, what is a region? A region is anywhere that you have to have 1 to 9 exactly once, so where digits can't repeat. So the reason the region is important here is we know that it must contain 1 of each digit. And so what does forcing mean? Well, forcing says that within that region, we look at where that value can be, and everywhere that value can be, no matter where it is, it forces a certain elimination. And then the word chain means that we couldn't do it. If it was just region forcing, that's what we would normally call pointing, where they just directly see something. So like what I did with this 7. these 7s are technically a region forcing, but we just call it pointing, because no matter where the 7 is, this one can't be a 7. So it's kind of the reverse way of seeing the contradiction, where if I fill a 7 here, then there's nowhere in this box to fill a 7, so I can't. So it's the opposite, saying no matter where I put a 7 in this box, this can't be a 7. So what I'm going to, but with a chain at the end says, we can't just directly see it. We have to go through some kind of chain in order to actually determine that. So what I'm going to do is I'm going to look at where 4s are in column 3. And I think it would be interesting to see if anyone figures out what region forcing is actually happening here. So I'll give you a second to pause if you want to and look at it. Again, we're looking at 4s in green. I will give a hint now, and I will say that we are eliminating a 4 from blue here. So this blue is going to have a 4 eliminated from it. Do you see it yet? The next hint is it involves these 4s up here, which I can actually corner mark. All right, so now I'll just give it to you. So where could 4 be? Well, either of these two 4s sees this blue cell. So if either of these two ends up being 4, then blue is not 4. So that's easy. But what about the third case? What if this one's a 4? Well, this 4 sees this 4 by knight's move. And 4 can only be in 2 places in the box or the row. And so that would place a 4 here. And guess what? This 4 also sees blue. So no matter which one of these is 4, I end up with blue not 4. So again, we can look at that in reverse as a contradiction if that's preferable. If I place a 4 in blue, immediately I have to force, we can see this in a couple ways, but immediately I would not have a 4 in either of these two, and I would not have a 4 in here. So for this row, I'd need a 4 here, and for this column, I'd need a 4 here, and those would see each other. Another way to see that would be I'd place this 4 and this 4, and then now there's nowhere to place 4 in this column. Or if you want, we might be able to do a region forcing here, because what we could say is if this one's a 4, it sees blue. Or otherwise, this one's a 4, which sees this one, which leaves a 4 in one of these two, both of which see blue as well. So there's a lot of ways to see the exact same technique. I think it's not that hard to understand, at least once it's been pointed out. And so ultimately, we can just remove 4 from the blue clones here. All right, so the next thing that we're going to do is we're going to keep focusing on 4s. And we're going to see where 4 can go in... I'm just going to use green again. This is where 4 can go in column 4. This is where 4 can go in column 5. And we already have penciled, this is where 4 can go in column 6. And we're going to do another fin swordfish. And I'm curious if you can start seeing these fin swordfishes now that I point them out. What are my cover sets here? Because it's a little bit of an odd one. This one's definitely a sashimi swordfish. And what sashimi means is that it's not really a swordfish, because without the fins, you end up basically with just singles. So if the swordfish without the fins devolves into either an X-wing or singles, then it's not really a swordfish. So it's called sashimi swordfish. Anyway, I'm going to cover with row 1, row 4, and row 6. So these two are my fins. They both see this cell, and it's in row 6, which was covered by my fins sashimi swordfish thing. And so this can't be a 4. So I'm eliminating 4 from here. And now we're going to do another cell forcing chain here. So I'm gonna highlight a few more cells here that can be 4. We are going to be eliminating from this red cell here. We're eliminating 4. And that's going to be huge because we now will have 4 in nice positions in column 4. So how are we going to do that? Well, it's going to be another region forcing chain. And I am a little bit curious if you can see which region we're going to use for that. There's a few candidates that we could think about. And in fact, there's a couple that we could use. So I'm curious which one you choose. I'm going to choose row 5, but I think you could also use column 5. So how does it work with row 5? Well, this one's obvious. If this one's a 4, red is not 4. How about this cell here? If this cell's a 4, well, we're using the same technique here. This one's not a 4. This one is a 4. It sees red by knight's move. So if this one's a 4, this one's a 4, red's not a 4. So now we just have to prove this one. If this one's a 4, well, now this one's not a 4, and if we know in column 5 we're limited to 2 spots, that means this one is a 4. That's in the same box, so this one cannot be 4. So the question is, could we use this region forcing? This one obviously eliminates red. If this one's a 4, these two are not, which means this one's a 4, which means this one's a 4, and that does see red. So we could have also used column 5. So whichever one you want to choose. Either way, this red cell is not a 4. So now that we have eliminated this cell from column 4, we now are limited to these two cells, which this is a standard anti-knight trick where these two, when they're separated like this, they see both of these. So now yellow cannot be 4. And that gives us a 7-9 pair in column 3. So now these two cannot be 7 or 9. That gives a 4-5 pair. And so now the 4-5 pair in the box eliminates a 4 from there. Now the 7-9 pair also sees this cell here, so let's not forget about this cell. So now that can't be 7 or 9, what can it actually be? Well, it can't be 1, 2, or 3. It could be 4 or 5. It can't be 6, and it can't be 7, 8, or 9. So it is just down to 4 or 5, which is pretty awesome. And also what we can see is in this row here, in row 5, where can 4 go? Well, now it's pretty clear that 4, if I unhighlight this green here, is limited to just these two in the box. And so now this one's not a 4. And by unhighlighting that, we have now made a single 4 in column 5, which we luckily already still had highlighted in green. So a 4 goes here, 2 goes here. That finishes our 2 X-Wing. And so now we can see with this 1-5 pair in the box, we're down to just 6, 7, or 9 in the box. And so 7 in the triple is actually limited to column 9. So, oops, I typed 9 instead of 7. Those see down to this 7, and now these 7s are limited as well. And this is a anti-knight pattern here. These two 7s both see these two cells. And so what we can say is 7 is limited to these two. There's also just limited in the column, but this is more fun, right? And the next step is going to be probably the last really fun one, but it is pretty fun. So I'm gonna unhighlight these greens because we're gonna use green for our patterns consistently here. So the question we're going to ask is, where do 7 and 9 go in columns 3 and column 4? Well, column 3 is obvious. We've got these two. And actually, we've handily gotten purples and yellows. We've proven are different digits. So those are the 2 7 9s. And so, for example, this cell here can't be 7 or 9 because it sees both a purple and a yellow. And so now purple is going to be one of these. We don't actually know that blue and orange aren't purple. But anyway, that's beside the point. Let's look at where we can actually put 7 and 9 in these columns. Well, we are actually limited now to these green cells for 7 and 9. So the interesting thing about this here is we could actually treat this like an X-Wing if we wanted to, a really weird one. Since I eliminated this 7-9, it's no longer necessary. This would have been green otherwise. We could have drawn this X-Wing here. And you can see that all of these cells actually see this center cell in box 1. So if I cover like this, I cover an X-Wing, I have 3 fins, and they all see this cell, limiting both 7 and 9, since we have 2 overlapping fishes here. Without this green here, it's probably a little bit easier to see that this has to be one of the 7-9s. This has to be the purple one. And the yellow 7-9 in this column is actually one of these 3. And so this cell sees a purple 7, 9 in its box, and it sees a yellow 7, 9 in these 3 cells. No matter where it is in these 3 cells, it sees it. So however you want to see that, this cell can't be 7 or 9. It is a 4, which is very nice. This is now a yellow 7, 9. We can get rid of our greens here. That sees down. This is purple. This is yellow. Any excuse to color, right? And so now it should be pretty clear to see that blue can no longer be 9 because it sees a purple and a yellow 7, 9. So blue is 5, which is great because now we know orange is not 5. These can't be 5 either. This 5 sees here, placing a 4. That's a 5. This 4 sees the corner mark 4s. That places that 4 there. Now what we can do is we can look at column 1 and see that the remaining 2 cells here are 4 and 6. Which means the remaining cells for this column are 3, 7, and 9. One of them is going to be purple. This cell here can't be 7 because it sees 1. So there's a purple in one of these 2. We can also fill column 5 here. This is a 6, 7, or 9. And we can take a look at this column here, and we have a 6, 9 pair. So this cell can't be 6 or 9. It's a 5. And so now, where do 4 and 5 go in this row? Well, now that I have 4 and 5 placed in this box, they can't go here. None of these are 4 and 5 because of here, so basically these line up. And that places a 4, 5 pair here, so this cannot be 9. That leaves this cell as a 1, 7, or 9, but we already showed it couldn't be a 7, so it is a 1 or a 9. So now what we're going to do is we're going to look at row 8, and we're just actually, why don't we just fill this whole box? And if we look at box 6, we can actually see that 6s are limited to these 2 cells. So those point down, eliminating 6s from here. And now we have magically a 3, 9 pair. So this cell's not a 9. And that's actually key, if you believe it. Eliminating 9 from here means 9 is now limited to these 4 cells in box 9. Do you see what all 4 of those cells look at? If you said yellow, you win a prize. These 2 see it in the row, and these 2 see it by knight's move. So yellow can no longer be a 9. It has to be 7, which means purple is 9. We don't know about orange yet. But what that means is this is now a 3, 9 pair as well. We can get rid of our purple and yellow coloring, no longer useful. And we can do some cleanup here. This one's no longer a 7. This 7 sees over. That places this 7. That places this 7. That set sees this 7 by knight's move. That places this 7. Places this 7. This sees a 9 now. That's a 6. That looks down. This is a 4. 6 and 4. And you can probably tell we are starting to clean up quite a bit. This sees a 6 as well. So now where does 6 go in the box? It must be orange. So we place those as 6. Alrighty. So now this is 4 and 9. And this basically just finishes up however you'd like to. The 9 in the box goes here. That puts a 6 here. That puts a 6 here. This is a 1. This is the 9. The 1 sees up, putting 5 and 1. We finally have our 1 X-Wing resolved. It took the whole puzzle. This 5 looks down, making that a 9. That's 3 and 5. This is 9 and 3. And finally up here, this is a 6 and this is a 5. And there we go. That is how you solve Beetle Knight. I hope you enjoyed this showcase of anti-knight techniques. We had a lot of finned fish. Tons and tons of finned fish. We had some fun logic with unorthodox tuples. We had some more standard anti-knight pointing, some interesting anti-knight pointing that maybe you hadn't seen before. And we had a couple region forcing chains, which were interesting. And of course, we had our intro where we had a discontinuous nice loop, which resolved this 1 and this 2. And you got to see the power of the 1s and 2s in this specific orientation, which actually places a ton of 1s and 2s around the grid and really limits them. So I hope you enjoyed this. If you're not subscribed, please remember to subscribe. I stream on Thursdays and Saturdays. You can see my stream schedule as a community post on my YouTube. I also have a Discord server that I share with some other Sudoku YouTubers, specifically Bremster,Zetamath, and Scott Storsall. And so you can check the description below if you'd like to join my Discord server and hang out with us. I also have a Patreon if you'd like to join my Patreon and support me either because of my YouTube or because of my solver or a combination thereof. It's a great way to support me on a monthly basis. I'm still experimenting with Patreon rewards, but I did post a solve ofZetamath's puzzle called Antimatter recently to my channel. And it took me 2 hours and 40 minutes to solve that. And I cut the video down to 1 hour and 40 because there was about an hour of footage where I wasn't making a whole lot of progress. But if you want to see that entire 2 hour and 40-minute video, my patrons have access to the uncut footage there. So if that interests you, maybe consider joining my Patreon. It's a choose your own price Patreon. There's just one tier. You contribute however little or much as you want. I believe the minimum is $1 so per month, and you get access to that. So other than that, thank you everyone for watching. I hope you join me on my streams or on the Discord or wherever else, and I will see you next time.